Yeah, students, today we are going to discuss what is the percentage composition and how to determine the empirical formula and the molecular formula from the percentage composition of a given substance. So, we have learned what is molecule, what is compounds. So, in a given molecule or in a given compound, the formula contains fixed quantities of the combining atoms. So, first of all, to find the molecular formula, we should have the percentage composition of the given components present in a given molecule of the substance. Once we have this percentage composition, from the experimental data, we have to derive the molecular formula. So, to derive this, first requirement is we have to find the percentage composition. So, let's start with percentage composition. Percent composition. So, we are well versed or well aware of the term percentage. Percentage is defined as number of parts by mass of a component divided by total number of parts by mass multiplied by 100. So we define this percentage as number of parts by mass of a given component divided by total number of parts by mass multiplied by 100. So now we are having a molecule or substance. So for this molecule or compound, total number of parts by mass is nothing but the molecular mass expressed in terms of gram. So therefore the equation is number of parts by mass of a component divided by gram molar mass multiplied by 100. So for a given substance, we define total mass as gram molecular mass. So we can define this gram molecular mass if the atomic masses are given to you and the formula is given to you. So this is how we define the percentage composition of any component present in a given substance. Let's take this example. We have H2O molecule. Now in this H2O molecule, we have to find the percentage of hydrogen and the percentage of oxygen. So what is the percentage of hydrogen in H2O and the percentage of oxygen? Now percentage of hydrogen is mass of hydrogen divided by gram molecular mass of water. So if you look at this, in a given molecule of water, we have 2 atoms of hydrogen. So total mass of hydrogen is 2 into 1. Molecular mass of water is 18. So we have looked at this. So the percentage of hydrogen in water is, so this is 11 point something. Now look at this percentage of oxygen. So in this given molecule of water, we have hydrogen and oxygen. The percentage of hydrogen is 11 point something. If the percentage of hydrogen is 11 point something, then the percentage of water is, oxygen is 100 minus percentage of hydrogen. So this equals to 100 minus 11.1. So this is 9, 8, 88.89%. Or look at this, percentage of oxygen is mass of oxygen divided by gram molecular mass. So mass of oxygen is 16 because one molecule has one oxygen, and gram atomic mass of oxygen is 16. So molecular mass is 18 multiplied by 100. Is the same. So this is how we define percentage of the given components, that is hydrogen and oxygen, in water molecule. Take this second example. We have a sample of sodium sulfate with X water molecules of crystallization. So a sample of sodium sulfate contains some X water molecules of crystallization. This is a solid. This sample on heating loses 55.9% of its weight. Find the value of X. So we have a crystalline sample of sodium sulfate, X water molecules of crystallization. This substance, crystalline substance, on heating loses 55.9% of its given mass. So what is the value of X? That means how many water molecules of crystallization is present in the given sample. So we have to find percentage is given. So look at this question. So we have this sodium sulfate X water molecules of crystallization. Now these on heating, because we are heating the sample, so on heating these water molecules of crystallization will be removed, and what we are getting is sodium sulfate solid plus X water molecule that is being removed. Now look at this, the loss in mass is due to removal of water. So therefore loss in mass is due to removal of water. So if mass loss is due to removal of water, so the percentage loss in mass should be equal to the percentage of water molecule that is present in the given sample. So therefore that is percentage of water in this sample should be equal to loss of mass, percent loss of mass. So percentage of water, we have X times water molecule, mass of water molecule is 18, so we have 18 into X, that is the total mass of water, because each water molecule weighs 18 gram, the gram molecular mass. How many water molecule is there? X. So total mass of water is 18X divided by gram molecular mass of sodium sulfate 18X. Sodium is 23, sulfur 32, oxygen 16. So we have 16 into 4, 64, plus 32 plus 26. So therefore we have 26, 30, oh sorry, 46, 32, 64, 142. So this is 142 plus 18x. 143 is for sodium sulfate, 18x is for water, into 100 will be equals to 55.9. So look at this total loss in the weight of the given substance on heating is due to removal of water molecules of crystallization. So therefore, the percentage of water in the given sample should be equals to the percentage loss in mass. So percentage of water is mass of water divided by gram molecular mass into 100 is equals to 55.9. So on solving this, we'll find the value of x. So this is the number of water molecules of crystallization present in the given sample of sodium sulfate crystalline salt. Let me give you another example. Now we have a potato. A starch potato is a starch. A sample of potato starch on analysis gives potato sample, that is starch, contains 0.086% phosphorus by mass. So we have a sample of potato starch. Analysis of this sample shows 0.086% phosphorus by mass. If one molecule of this starch contains one phosphorus atom, then what is molecular mass of starch, potato starch? So we have a sample of potato starch. Now on analysis of this sample of potato starch shows 0.086% of phosphorus by mass. And we are also assuming the one molecule of the given starch contains one phosphorus atom. Then what is the molecular mass of the starch? Now says, look at this percentage. So percentage means total mass of the sample is considered to be 100 gram. So out of this 100 gram of sample, what is the mass of phosphorus? 0.086 gram is for phosphorus. That means 0.086 gram of phosphorus is contained or present in 100 gram of the sample. 0.086 gram of phosphorus is present in 100 gram of starch. So if 0.086 gram is present in 100 grams, so 1 gram of phosphorus will be present in 100 by 0.086. Now question says, we are assuming each starch molecule contains one phosphorus atom. So the gram molecular mass of phosphorus atom is 31 gram. That is the molecular mass of phosphorus. So 31 gram of phosphorus, that is 1 gram molecule, will be present in 100 into 31 divided by 0.086. So these gram is corresponding to one phosphorus atom whose gram molecular mass is 31 gram. So the mass containing 31 gram of phosphorus, which is equals to 1 mole of phosphorus or 1 gram atom of phosphorus, will be the molecular mass of the potato starch. So this is equals to molar mass of potato starch. So this is how we use percentage for solving problems. One more example that I'm going to take a base. Chlorophyll, the green coloring matter of plants, contains 2.68% by mass of magnesium. So chlorophyll, which is the green coloring matter of plants, contains 2.68% by mass of magnesium. Now question says calculate the number of atoms of magnesium present in 2 grams of chlorophyll. So again, look at this question says percentage. So the meaning of percentage, as we have used in the earlier previous example, total mass of the sample is 100 grams. So out of this 100 gram of the given sample of chlorophyll, what is the mass of magnesium that is present? 2.68. So 100 gram of chlorophyll contains 2.68. The question says total mass of chlorophyll is given as 2 gram. So in this 2 gram of chlorophyll sample, how many atoms of magnesium is present? So from the given condition of percentage, question says 100 gram of chlorophyll contains 2.68 gram of magnesium. So 100 gram contains 2.68. So therefore 1 gram will contain 2.68 divided by 100. Then 2 gram sample will contain 2.68 into 2 divided by 100. So this is the mass of magnesium present in 2 gram of chlorophyll. So therefore number of moles of magnesium, this is given as mass divided by gram molecular mass. So mass is 2.68 into 2 divided by 100. Gram molecular mass of magnesium is 24. So this is the number of moles of magnesium present in 2 gram chlorophyll. Now this number of moles is equal to number of atoms divided by Avogadro number. So therefore number of atoms of magnesium is equal to 2.68 into 2 divided by 100 into 24 into Avogadro number. So this equals to 2.68 into 2 into 6.02 into 10 to the power 23 divided by 24 into. So these mass atoms of magnesium is present in 2 gram of chlorophyll, which contains 2.68 mass percentage of magnesium. So this is the simple way how to use the percentage composition. Now once we define this percentage composition, the next problem is we have to define the empirical formula, and from this empirical formula we have to find the molecular formula of the given substance. So let's see how to find molecular formula. So next part of is determination of the molecular formula from the percentage composition. Determination of molecular formula. First of all, let me define what is molecular formula. Molecular formula shows the exact is a representation of a molecule which shows the exact number of the combining atoms present in the formula unit. So suppose we have a given substance, and the given substance contains a number of smallest unit which shows independent existence, and that smallest unit which is used for defining the properties of all that substance is what we call as molecule. So we have the smallest unit of a given substance which is used to define the properties of that substance and which also shows independent existence is what we call as the molecule. So molecule is a symbolic representation of a given molecule. So molecular formula is a symbolic representation of the given molecule of a given substance. So this molecular formula shows the exact number of the combining atoms present in the given formula unit. So we have to find. So for this determination of molecular formula, some steps has to be followed, and these steps must be followed in sequential order. So the first step is percentage of the given components. So in majority of the case involving molecular formula determination, the percentage analysis of the given sample will always be mentioned. If not mentioned, then we have to find the percentage of the given components present in the molecule. So first step is calculation of percentage composition. Second step, once the percentage composition of each and every combining atoms present in the given molecule is known to us, we proceed to the next step, and the next step is calculation of atomic ratio. Simply we say this is AR, atomic ratio. So let's define what is atomic ratio. This atomic ratio is nothing but percentage composition of the given component percentage composition of any given component divided by its atomic mass. So percentage of any given component divided by its atomic mass will give a ratio which is defined as atomic ratio. So we have to find the atomic ratios of all the given components whose percentage is defined. So we'll get atomic ratios of each and every component present in the given sample. So once we define this atomic ratio, we have to find simple atomic ratio SAR. So the first second step is find the atomic ratio by dividing the percentage of given component divided by its gram atomic mass. Once we define this atomic ratio, the next step is find a simple atomic ratio. So let's see what is simple atomic ratio. Simple atomic ratio is defined as the ratio defined in step 2, that is atomic ratio. Now we have to define these atomic ratios of all the given components by the least value of the atomic ratios. That value is defined as simple atomic ratio. That means we have atomic ratios of given components. From all these atomic ratios of the given component, find the least value of the atomic ratio. So with the help of these least value of atomic ratio, divide all the atomic ratios by the least value. That gives a ratio which is known as simple atomic ratio. And in majority of the case, this simple atomic ratio will come out to be simple whole number. If not whole number, then either we convert this fractional value into whole number. That is the next step. So simple atomic ratio is atomic ratio of components, that is defined in step 2, divided by least value of atomic ratios. So we have defined atomic ratios. From this atomic ratio, take the smallest value, that is the least value, and divide atomic ratios of each and every component by this least value, and this gives you a value which is known as simple atomic ratio. This is most of the case, this comes out to be whole number. So once we have this whole number, we can proceed to next step. If this simple atomic ratio does not involve whole number, some of the simple atomic ratios comes out to be fraction. So we have to convert this fractional value into whole number. So number 4 is whole number ratio. So we have to define this whole number ratio. So suppose look at this simple atomic ratio that we define in step number 3 comes out to be fractional value. Now we have to convert this into whole number ratio. So because in any given formula we cannot have a fractional value of the combining atoms, this has to be simple whole number ratio. So we multiply this simple atomic ratio by smallest integer so that it is converted into a whole number. So we have to start from the smallest possible integer, that is starting from 2. So suppose the simple atomic ratio comes out to be 1.5. So we have to convert this 1.5 into some whole number ratio. So we can convert this 1.5 into whole number ratio by multiplication with 2. So if you multiply this 1.5 by 2, this comes out to be 3. So if you multiply by 2, then all the simple atomic ratio should also be multiplied by the same value. So this whole number ratio is equal to simple atomic ratio by some integer. Means at any cost we have to convert this fractional value into whole number ratio. Once we have this whole number ratio, we define a formula which is known as empirical formula. Now let's define this with what is the meaning of this empirical formula. Empirical formula represents the simplest ratio of the combining atoms. the simplest ratio of the combining atoms in a given formula is what we call as empirical formula, whereas the molecular formula represents exact number of atoms present in the formula unit, whereas this empirical formula represents the simplest ratio. So this is simplest the ratio of combining atoms. The simplest ratio of combining atoms gives you empirical formula. Take this. So we have H2O2, hydrogen peroxide. So this hydrogen peroxide is the molecular formula of the sample, that is hydrogen peroxide. Now look at this. In this, look at this, we have 2 oxygen, 2 hydrogen, so 2 is a common. So there is a common factor, that is HO multiplied by 2. So this HO, this represents the simplest combining ratio of atoms. So this simplest ratio is what we call as empirical formula. So from this whole number ratio, we have to derive empirical formula, and this from this empirical formula we have to derive the molecular formula. So look at this. Therefore, look at this empirical formula. We have derived this whole number ratio. Suppose this compound contains some X and Y. So we have to derive the ratio of X and Y. So we have defined whole number ratio. So write the combining atoms side by side and place this whole number ratio as a subscript, lower right hand subscript. So we have to write whole number ratio of X. We have to write whole number ratio of Y. So this gives you the simplest combining ratios of atoms, that is defined as empirical formula. So once we define this empirical formula, we have to define the molecular formula, that is the last step. So molecular formula, that is MF, is equals to sum factor n multiplied by empirical formula. So we have this empirical formula multiplied by sum factor, that is, so we have to define this sum factor. So we have this empirical formula, multiply this empirical formula by sum factor n, and that gives you molecular formula. So this, you have to define this n. So this n is equal to molar mass divided by empirical formula mass. So the ratio of molar mass to that of empirical formula mass. That means molar mass of the given substance divided by the empirical formula, because we have defined this empirical formula. So we can easily define the empirical formula mass. So take this ratio, that is out to be n, and this n is equals to this n. So this is a whole sequence of steps that is used for defining determination of the molecular formula from the percentage composition. So first step is we have to find the percentage. From the percentage we have to define atomic ratio. So atomic ratio is percentage divided by gram atomic mass or atomic mass. Then we have simple atomic ratio. Simple atomic ratio is atomic ratios of the given component divided by the least value amongst the atomic ratios. In most of the case, this comes out to be whole number ratio, but if not, convert it to whole number ratio by use of a multiplication with a simplest integer. Then we have defined empirical formula. So write the atoms side by side and place the whole number ratio of each and every combining atom as a lower subscript. That gives you simplest formula, that is known as empirical formula. And the final step is molecular formula. The molecular formula is n times empirical formula, where n is molar mass divided by empirical formula mass. Now let's use this sequence of steps to solve molecular formula. I'll show you some examples. First, two oxides of a metal M contains 50% and 40% of metal. So we have a metal. This metal forms two oxides. In the first oxide, the percentage of metal is 50. In the second oxide, percentage of metal is 40. Find the metal oxides. You have to find the metal oxides. So we have looked at this. Metal contains 50% as well as 40%. So the first oxide, this is the first oxide. Percentage of metal 50. Then percentage of oxygen will be 50. That means if we take 100 gram of the sample, so out of this 100 gram of the sample, 50 gram is metal, 50 gram is oxygen. So that means 50 gram metal combines with 50 gram. So 1 gram will combine with 1 gram. So look at this. 50 parts of metal combines with 50 parts of oxygen. So therefore one part will combine with one part of oxygen. So the simplest formula is MO. That is 50-50 ratio. Second, percentage of metal is 40. Then the percentage of oxygen is 60. Percentage of oxygen 60. That means 60 parts by mass of M combines with 60 parts by mass of oxygen. So one part will combine with 3/2 parts of oxygen. So the simplest ratio is M. So convert this into fraction into whole number ratio. This comes out to be N2O. So if the first oxide is MO, second oxide is N2O. This is one example. Then let's take some other examples also. An organic compound contains the following: carbon 49.3%, hydrogen 6.84%, and the remaining, that is oxygen 43.86. If the vapor density of compound is 73. Find the molecular formula. What is the molecular formula of the compound? So, percentage composition of the component, that is carbon, hydrogen, oxygen. That means the organic sample contains carbon, hydrogen and oxygen. So these sample containing carbon, hydrogen, oxygen percentage are given as 49.3, 6.84 and 43.86. Vapor density of the compound is given as 73. So find the molecular formula of the given compound. So let's see how to proceed. So for this type of questions, I request you to proceed in the same fashion as I'm doing. So we have elements carbon, hydrogen and oxygen. We have percentage, then we have to define atomic ratio, then simple atomic ratio, then we have to define whole number ratio, then empirical formula. So percentage of carbon is 49.3, hydrogen 6.84, oxygen 43.86. So once we have this percentage of the given components, we have to convert this percentage into atomic ratio. So atomic ratio is percentage divided by gram atomic mass. So carbon atomic mass is 12. So we have 49.3 divided by 12. Hydrogen 6.84 divided by 1. Atomic mass of hydrogen is 1. Oxygen 43.86 divided by 16. This is the atomic ratios of carbon, hydrogen and oxygen. 49.3 divided by 12 will 4 is 48. 48. So this is 4.1. 12 4 is 48. So 1.3, 12, approximately 0.1. 6.84 divided by 1. So this is 6.84. 43.86 by 16. 16 into 4. 16 into 3, 48. So this is coming around 43.86 divided by 16. .7. So approximately 2.74. So these are the atomic ratios of carbon, hydrogen and oxygen. So out of these three values, the least value is 2.74. So we have to divide these atomic ratios of all these given component divided by the least value to get the value of simple atomic ratio. So this is 4.1 divided by 2.74. 6.84 divided by 2.74, 2.74 divided by 2.74, so this comes out to be 1. 6.84 divided by 2.74, 2 3 is 6, so this is 2. This is coming around 2.49. 2 to the 4. This will be approximately around 1.49. So simple atomic ratio of carbon, hydrogen, oxygen. This is 1.5. This is 2.5. This is 1. Now look at this, we have to convert this into whole number. So multiply these simple atomic ratios by 2. So we are looking at this 1.5 into 2, 2.5 into 2, 1 into 2. So 1.5 into 2, this is 3, 2.5 into 2, 5, this is 2. So we have this simple whole number ratio of carbon, hydrogen and oxygen. So therefore, empirical formula is we have carbon, we have hydrogen, we have oxygen. Whole number ratio of carbon is 3. Whole number ratio of hydrogen 5. Whole number ratio of oxygen, this is the empirical formula. Now once we have this empirical formula, next step is molecular formula. What is we require? The value of n. So therefore look at this empirical formula mass. We have this formula. So 3 into 12 plus 5 into 1 plus 2 into 16, 36 plus 5 plus 32. So this is 73. This is empirical formula mass. So therefore, value of n is molecular mass divided by empirical formula mass. So molecular mass, look at this question said is vapor density. So vapor density is to be converted into molecular mass. We have discussed earlier. Molecular mass is 2 times vapor density. So therefore, 2 into 73 divided by 73. So the value of n is 2. So therefore, molecular formula of the compound is 2 into empirical formula. So multiply this by 2. So this is 2 3 are 6, 2 5 are 10, 2 2 are 4. So this is the molecular formula of the given compound with this corresponding percentage composition. So this is how we define this percentage into the molecular formula by using this sequential steps. Let's solve some more examples so that we can easily know how to proceed. Question says a compound of carbon, hydrogen, nitrogen contains these elements in the ratio 9:1:3.5. Find empirical formula, molecular formula if molar mass is 108. Molecular formula is given. Combining atomic ratios of the elements is given as 9:1:3.5. What is the empirical formula? And from this empirical formula, find the molecular formula. So look at this. This is percentage ratios of the combined elements. So we have carbon. This is element. We have atomic ratio, simple atomic ratio. We have whole number ratio. Then we have empirical formula. So we have carbon, hydrogen, and nitrogen. Atomic ratio 9/12, 1/1, 3.5/14. So we have atomic ratios of carbon, hydrogen and nitrogen. 9 by 12, 7 to 14 to 0.7. So this is 0.75. This is 1. 3.5 by 14, so 0.2. 0.25. So we have atomic ratio of 0.75, 1 and 0.25. So out of these three atomic ratios, the least value is 0.25. Now to convert these atomic ratios into simple atomic ratio, we have to divide these atomic ratios by the least value. So therefore look at this. 0.75 divided by 0.25, so this is 3. 1 by 0.25, that is 100 by 25, that is 4. 0.25 by 0.25, that is 1. So we have this simple atomic ratio. It's like this whole number ratio, so we don't require this whole number ratio. So therefore look at this. Not applicable. So empirical formula is, so we have carbon, whole number ratio is 3, hydrogen is 4, nitrogen is 1. Once we have this empirical formula, is to be converted into molecular formula. So for this we require empirical formula mass 3 into 12 plus 4 into 1 plus 1 into 14. So this is 36 plus 4 plus 14, 54. So therefore the value of N is, molecular mass is given as 108, empirical formula mass is 44, so this is 2. So therefore molecular formula of the given compound is N into empirical formula, so N is 2. Empirical formula is C3H4 N1, so this is C6H8 and this is the molecular formula of the given compound. So let's solve some more examples. Next question. So question says a welding gas which is made up of carbon and hydrogen only with this formula CXHY on complete burning with oxygen gives you 3.38 gram of carbon dioxide and 0.69 gram of water molecule as the only product. A volume of this 10 liter of this gas CXHY at STP weighs 11.6 gram. Then find the empirical formula, molecular formula and the molar mass of the given substance. So question says we have this CXHY, this gas on complete combustion with oxygen gives you carbon dioxide gas and H2O. No other product is formed along with this carbon dioxide and water. So look at this. The carbon present in carbon dioxide is coming from carbon present in this welding gas CHSY, and the hydrogen present in water molecule is coming from this CXHY. So that means mass of carbon dioxide and mass of water is given. So the number of moles of carbon in carbon dioxide will be equal to number of moles of carbon present in CXHY. Similarly, the number of moles of hydrogen present in water should be equivalent to number of moles of hydrogen present in CXY. So look at this. Mass of carbon dioxide is given as 3.38 gram. Water is 0.69. Therefore, number of moles of carbon dioxide is equal to 3.38 divided by 44. Number of moles of water, this is 0.69 divided by 18. So if you look at this, one molecule of carbon dioxide contains one carbon atom. That means if one molecule contains one carbon, then two molecules will contain two carbon, five will contain five. So one mole carbon dioxide will contain one mole of carbon. That means the number of moles of carbon dioxide will be equal to the number of moles of carbon present in the given sample of carbon dioxide. And all this carbon in carbon dioxide is coming from carbon present in the given organic compound. So therefore, look at this. This is equal to number of moles of carbon in carbon dioxide. Now, since all this carbon dioxide is coming from the organic compound, that is the welding gas, so this must be equal to number of moles of carbon in CXHY. So therefore, number of moles of carbon in CXHY is equal to 3.38 divided by 44. So this is coming around 0.076. Now, one molecule of water contains two hydrogens. Therefore, look at this. Number of moles of hydrogen in water will be equal to 2 times number of moles of water, because one molecule contains two hydrogen atoms, so one mole will contain 2 moles. This must be equal to number of moles of hydrogen in CXHY. So this is equal to 2 into 0.69 divided by 18. Again, this is coming 0.076. So we have number of moles of carbon, number of moles of hydrogen. So first part. So mole ratio is 1:1. So therefore, empirical formula is CH. Number of moles of carbon is 0.076. Number of moles of hydrogen is 0.06. So synthesis ratio is 1:1. So we have this empirical formula. Empirical formula mass will be equal to 2n plus 1, that is 30. So we have empirical formula. Now the second one is molar mass. We have a gas. This gas at STP weighs 11.6. This 10 liter of this gas weighs 11.6. So 1 mole of any gas at STP will always occupy 22.4 liters. So we have to find the mass corresponding to 22.4 liters. So look at this, 10 liter weighs 11.6 gram. So 1 liter will weigh 11.6 divided by 10. So 22.4 liter into 22.4 divided by 10. So mass corresponding to 22.4 liter, this is always what you call as gram molecular mass. So every 1 mole of every gas at STP will always occupy a volume of 22.4. So the mass of 1 mole is equal to gram molecular mass, or we say mass corresponding to 22.4 liter of any gas at STP is equals to gram molecular mass. So we have this gram molecular mass. Now we have empirical formula, we have gram molecular formula, a mass, then we have to find the molecular formula. So 11.6, let's find out this value. $25.9 and 4, and this is 26. So the final one is how to find the molecular formula. Third part of the question. For this we have to find N. So N is molecular mass divided by empirical formula mass. So molecular mass is 26. Empirical formula mass is 13. So this is 2. So therefore molecular formula is equal to 2 times empirical formula. So we have 2 into C1H1. So that is C2H2. That is acetylene. Acetylene is the gas whose given data is given. So let's go for one more problem to find the molecular formula from the percentage. Find the empirical formula of a compound containing 50% X whose atomic mass is 10U and 50% Y whose atomic mass is 20U. The formula contains X and Y. Percentage is given as 50%, 50%. Atomic mass is given as 10U and 20U. So we have X, we have Y. Percentage is 50, 50. So therefore atomic ratio is percentage divided by atomic mass. So simplest ratio, simple atomic ratio. Atomic ratio divided by the least value. So 5 divided by 2.5, that is 2. 2.5 divided by 2.5, that is 1. So we have simple ratios, 2:1. So therefore, empirical formula of the given compound is H2. This is the formula of the given compound with this percentage composition. So this is how we define molecular formula from the percentage composition. So for this, the requirement is we need to have the percentage composition. We need to have the gram atomic mass of the given substance. So from this percentage, we convert into atomic ratio. Then again, this atomic ratio is converted into simple atomic ratio. In majority case, this comes out to be a whole number ratio. If this simple atomic ratio comes out to be some fractional value, then we convert into whole number ratio by multiplication with the simplest integer. Once we have this whole number ratio, we convert this into empirical formula, which shows the simplest ratio of the combining atoms in the given formula unit. Once we have this empirical formula, we convert this empirical formula into molecular formula. So empirical formula multiplied by some factor n, that is known as molecular formula. So we define this n as molecular mass divided by empirical formula mass. So but for this, we have to proceed in the sequential steps. Hope you understand the process for determination of molecular formula.